Today we're going to talk about chapter 6.9. We're talking about modeling with polynomial functions. Really what we're talking about is writing the equation of a polynomial function once I give you the graph. So I've given you the formulas and you guys have graphed in the last couple sections. Today, now I'm going to give you the graph. You're going to tell me what formula is going to give me that. So, if we're going to write the cubic function that I have shown here, what are some important points that could help us write the formula for that function? Yeah. These x-intercepts, how do I normally take care, or how could I show that I have those x-intercepts in my graph? How do I show that I have an x-intercept at -3? Yeah, so I'm going to have something that says x plus 3 to take care of that -3. Remember, we're always subtracting here. How would I handle one at +2? I'm going to have x minus 2. And what about one at 5? X minus 5. Okay, so we're going to use those x-intercepts to help us write that formula. This looks like something that I gave you guys last week, right?
Yep.
Okay. The only difference is sometimes I would put a number out front here, right? Whether it was like a 2 or a half. I think we did a quarter in class. Okay. We need to account for that. We don't know whether this has one of those numbers, so we're going to put in the letter A. Okay. A is just our stretch factor. So what that means is I can start with a basic cubic graph, but do I have that number out front where I multiply everything by 2 at the end after I plug in my x values if I'm looking for my y? I need to figure out if that stretch factor is there, making that graph either get really skinny or really wide. So let's take a look at this here. Blake started out. Sets it up. Y equals a times all of our x-intercepts. I don't tell you they're x-intercepts, but how can you tell that they are? Good. Your y value is always 0 at your x-intercepts. So x minus a negative 2 is going to give us that x plus 2, x minus 1, x minus 3. We're going to use the 0, 2 point. Now I gave you the y-intercept. Okay, plug in 2 for y, 0 for x. You end up with 2 is equal to 6a. Divide both sides by 6, you get 1/3 for that a value, or your stretch factor, and plug it back into your formula that you had before, replacing a with 1/3. Questions on that? All right. So the next thing we want to do is we're going to look at what's called the triangular numbers. Have you guys heard of those to camp? So here is a formula for the nth triangular number. So if you want the 5th triangular number, you would just plug in 5 for n. We want to show that this function has constant second order differences. But first, we should probably figure out what the triangular numbers are. Okay? So how many, really what we're trying to do is we're trying to make triangles. So the first triangular number, I like to show these with dots. Okay? It's just a single dot by itself. The next one, I add 2 dots below that to make another triangle, but bigger. So how many dots do I have here? 3. 3. 3 is the second triangular number. Okay? How am I going to get to the next triangular number, you think?
Add 3 more dots.
Okay? We're going to add 3 dots at the bottom. So I'm going to have my pyramid is now going to look like this. So how many dots do I have in total? 6. 6 is going to be the third triangular number. We're going to add 4 to the bottom. Okay, so how many do I have now? 10. Let's do one more. Okay, what am I going to add to the bottom? I'm going to have 5 on the bottom. So they're triangles, hence why they're called triangular numbers. Okay, what do you think the next triangular number is going to be?
21.
21. It is almost like a pattern. Okay. So what we're going to do is we're going to take a look at these numbers. So we're looking for constant second order differences. What does difference mean? What operation?
Not the same. Dividing.
Subtraction. Okay. So if I take 3 minus 1, what do I end up with? 2. 6 minus 3. 3. 10 minus 6. 4, 15 minus 10, 5, 21 minus 15 is 6, okay? It helps me. The ones with the dots, it helps. So it helps me, yes. Okay, so right here, this is our first order. These are our first order differences. We haven't done anything with it. So we've gone through this subtraction once. We want to show that it has second order differences. So what do you think we're going to do again? We're going to subtract again. 2 minus 3. 4 minus 3. 1. Okay? So there's our second order. Okay? Is that constant second order differences? So is 1 constant? Yep, it doesn't change. It's the same difference between numbers. That's constant second order differences. So, yeah, all of this, the whole process is going to be your answer, as opposed to just. Yep, so we're looking for that constant, and they'll usually tell you second, third order differences. But, yep. So these help us with figure out what the triangular numbers are.
How do you, so you just like put 1, so you always just do that?
Mm-hmm.
So it's only 1, 2, 6, 10.
Yep. So those are your triangular numbers. It's how many dots you would need to make the next bigger triangle.
What if, like, the function ever change?
No, because this is, no matter what, this is how you find triangular numbers. Guys, I'm trying to answer questions. So this is just how you find triangular numbers. They give that to you. So they could do different types of numbers, though, which then your function would change, whether it's perfect squares. After a certain, I think they have constant second order differences as well, or something else. All right. So, couple properties of finite differences here. If a polynomial function has degree n, then the nth order differences, values for equally spaced x values are non-zero and constant. So we had a second degree polynomial here in our function. We have that n squared. We equally spaced it from one triangular number to the next. Okay, we ended up with non-zero and constant numbers for those second order differences. Also, if you can work backwards with it is really all this is saying. So if I tell you that it has second order differences, then you can use it to write the function can be represented by a polynomial function.